a third-year electrical engineering major here at UCSB, and I've been working with my mentor Robert Zhang in the Professor John Bauer's lab in the electrical and computer engineering department, working on the project Electronics and Photonics Design Automation. So how many of you like to make long-distance phone calls or video calls? A lot of you, I see. This is made possible through fiber optic transmission of data, and this is using light. So the basic idea behind this is that the light travels enters one end of the fiber optic cable and reflects within the cable and exits to the other end, through where it's transmitted and read as data. So because light travels at such a fast speed, it allows the data to transmit very quickly. And along with this, because optical signals are harder to tap into compared to electrical signals, it also makes it a much better way of using it in electronics. It's also low energy and much smaller compared to electrical devices. So it's already being used in communication and biomedical devices, but there are many applications of optical electronics still yet to be determined. And with my research this summer, I plan to make it much easier to integrate optoelectronics into our society. So in order to do this, I've been working with optical fibers in MATLAB in order to create, develop and implement an algorithm that will allow for multiple automated test setup for multiple devices in a time-efficient manner. By testing multiple devices, we're able to characterize the devices in order to develop a PDK or a process design kit, which users can use in order to create their circuits before actually fabricating them in an actual clean room. So to start off with, what is a PDK and why is it important to us? A PDK is basically a library of devices that is made after characterizing devices, and users can use it in order to create their circuits on a computer before simulation. And by doing this, they can worry about more of the design and creating it smaller rather than actually worrying about the physics behind the device. So the basic process, as you can see in the flow chart, is that the user can input his or her design into the circuit simulator, which then goes to the mass generator and is finally fabricated in a fabrication facility, and then they get the chip. So this is essential in the process because it allows for a much more time-efficient and accurate manner of creating circuits, photonics integrated circuits. So in order to measure these devices in a time-efficient manner, I've been working in the lab to create an automated alignment algorithm that we can use to measure these devices. So the setup that I've been working with is the one shown in the schematic, where the laser goes through the fiber optic cable on one end of the device and enters and goes through the waveguide on the device, and then exits on the other end where it's detected by the photodetector. So the idea behind the algorithm is basically that first the user can manually align their first device, and then the motors automatically move in order to find the optimal alignment, and then the data is automatically recorded and the stage automatically moves to the next device, and the process repeats until all the devices are measured on that chip. So as you can see in the real picture from the lab, these are the motors, and this is the chip that is placed on the stage. And this is the optical fiber that refers to the laser, and the optical fiber that refers to the photodetector. So one of the devices that I've been using with this test setup is the multimode interferometer 2x2 50/50. So the 2x2 basically means that there are 2 inputs and 2 outputs. And basically the light goes in through one end and reflects within this, and based on the length, we can get different outputs out of both of the outputs of the MMI. So by using this, we created this device that my mentor created. And it basically inputs the light through port 1 and travels through the MMI where it's coupled and has 2 outputs, which go into a UMZI, which is an unbalanced Mach-Zehnder interferometer. And because it's unbalanced, there's basically a phase shift, which goes back into another MMI and is read at the outputs of 3 and 4. By doing this, we can determine the power splitting ratio of the device and see if it matches what we want it to create. And by doing this, we can also characterize the MMI in order to actually create the PDK. So So we found this graph after putting the laser at port 1 and the photodetector at port 3. We were able to get this graph, which is after sweeping the wavelength, and found the wavelength versus power graph. And by using the max and min points of the graph, we were able to find the ratio that is used in this equation. And then we did the same thing for ports 2 and 4, and were able to find the ratio for 2 and 4. After plugging this in, we were able to find the power coupling ratio. So as you can see, this is a 50-50 device, so we were trying to get a 0.5 splitting ratio, which we were approximately able to get, but due to loss, it's slightly off, but as you can see, the device works pretty well. So after measuring multiple devices, we were able to see that smaller length and width of the MMI allowed for optimal power coupling ratio, and that the angle made no difference to the ratio. So another test setup another device that we used was the quantum dot laser. So the difference between a quantum well and a quantum dot laser is that a quantum well has electron holes confined within a one-dimensional plane, while this is medium, while the quantum dot is confined within the three-dimensional medium, which allows for it to work under less power, which is essential for photonics. So the basic structure that we used was that the laser and function generator would go into an amplitude modulator, which would create an optical signal going into the fiber optic cable and going into the device. And the electric probes basically, with the DC bias, put current across the NNP junctions, and we were able to calculate the magnitude and phase of the RF signal detected from the probe pad using the lock-in amplifier. So by doing this, in order to do this, we got data from some of my colleagues, such as Katie, who gathered data for the wavelength versus the gain graph, and from that we were able to find that the max gain for the laser was at 1.3 micrometers at wavelength, and another colleague gave us the threshold current using this graph, which is the current versus power graph, and gave us the threshold current at approximately 12 milliamps. So using these parameters, we were able to set our setup up in order to find the transparency current. And basically the transparency current is the point where the phase goes from negative phase to positive phase. And it's basically at the zero. So when the phase is at negative, it's absorbing light. And when it's at positive, it's emitting light and amplifying it. So the point at where it's zero is basically where we consider it to be transparent. So that can allow us to find other aspects of the laser later on. And we also noticed that the magnitude of the transparency current was at the lowest point at the transparency current. So using the data that we got from the transparency current, we were able to use the current and gain graph